Hello and welcome to part 4 of lecture 5 of ENGR 231 Engineering Statics. In this portion of the lecture we are going to get to applying moments and moment equations in 3 dimensions using Cartesian vectors, cross products, etc. So let's look at 3D moment vectors. So if I want to take the moment of a force about a point, there are 2 ways to do that. The first that we saw previously was to do more of a scalar approach, where you just directly multiply forces times distances or forces times perpendicular distances, either using trigonometry to get the actual perpendicular distance directly from the vector, or break the vector into its component pieces, its rectangular components, and then using perpendicular distances therein. Although, that's all fine, and I like that method especially for 2D problems or 2D systems, but when you start dealing with 3D systems, often the most convenient way to solve that is going to be to use a vector-based approach. So let's say you have a coordinate system, x, y, z, x, y, and z. And then let's say we have a point, some point A. We have some point A, and we have some point B, and then we have a force vector F, again not just a force, but a force vector F, and it has a certain line of action, extending backwards and forwards to infinity and negative infinity. A true line of action, not a line segment, but a line of action. Then I'm going to define a term r, and this is going to be a displacement vector, and I will describe each of these as shown below. We have a vector r. Now, the moment of a force about a point in vector form the moment of a force about a point is relatively straightforward. The moment, and this would be a moment about A, vector, is equal to r cross f. So it's simply the cross product of the force vector and the displacement vector. So now, I should give a note on each of these. So MA, this is the vector of the moment vector produced. And F is the Cartesian force vector. So the full force vector, and R is the, R is a displacement vector, but it is a displacement vector from anywhere along the basically from the point that you're taking a moment about, to anywhere on the force's line of action. It looks like antware. Anywhere on the force's line of action. And this is a bit counterintuitive, but it is true. It's just one of the natures of cross products. So in other words, if I let my r be from here to here, I'll get a moment. I'll get a certain value for the moment or a certain vector for the moment. If I take the cross product from here and I end it, the displacement vector, I take it from here to here, I'll get the exact same moment vector. If I take it from here to here, I'll get the exact same moment vector. Again, the vector needs to go from whatever point we're taking the moment about, but the endpoint can be absolutely anywhere along the force's line of action. And the reason that's beneficial is that oftentimes it's more convenient to take the moment or find coordinates at one point than another. Okay, so maybe we can work through a basic example. Let's go ahead and work through a basic example here. So let's say we have a force. I'll just do a rather generic example, or general example. So let us say we have a coordinate system like this, x, y, and z. Now, let's say I have a point A with coordinates of, I don't know, let's say 1 meter, negative 2 meters, or actually, no, 2 meters and negative 1 meter. And then I have point B with coordinates of, let's say, 2 meters, comma, let's say 2 meters, comma, negative 2 meters. Actually, no, I don't want to have the same in the y, so let's go ahead and say that's 3 meters just for fun, for a relative definition of fun. And to make the calculating the force vector easier, let me just go ahead and say that its line of action goes through the origin. I think by now you're pretty good at finding force vectors, or at least I hope so. And so we have some force vector F. It goes through the origin and through from the origin to point B, the force vector does, or its line of action does. And so force F passes from the origin, or force F's line of action through point B, and has a magnitude, of 10 newtons. I want to find the moment it generates about point A. The moment it generates about point A. So, so really this is a fairly straightforward problem. It's it can be a lot of work to do these, but working with a general force vector, it's really not too bad. Okay, so let's look at this. Now let's just go ahead and solve this. So solution. Basically, a lot of this is the hard part of these is just the building process, like developing the R, developing that, etc., etc. Now, let's see. So what could we do? First, I want to get the force vector. And this is going to be 10 newtons, but then it's times the lambda, or the unit vector of the force. And I'm just going to bake that into a single calculation here. The lambda is going to be the displacement vector from here to here, the line from the origin to point B, divided by its magnitude. So that would be 2 meters, comma 3 meters, comma negative 2 meters, divided by the square root of 2 squared plus 3 squared plus 2 squared. 2 squared plus 3 squared plus 2 squared. And so I'm going to go ahead and multiply all that out and get a single, meters would be, we'd have not side unit meters there. Meters become squared, then it comes out of the parentheses, or out of the root. And so I'm just going to go ahead and throw this into my calculator and get a final force vector. 2, 3, negative 2. And then divided by this, okay, so square root of, well, we have 2 squared plus 3 squared plus 2 squared, and that will be 17. Oh, that didn't need to use a calculator for that, that's for sure. So basically that vector, 2, 3, negative 2 times 10 divided by the square root of 17. And I'm just going to go ahead and do this as an ugly decimal. And this will come to this then comes to 4.85 newtons, comma, 7.28 newtons, comma, negative 4.85 newtons. Again, I think by this point you're pretty good at finding force vectors, or at least hopefully. I know a summer class like this does move pretty quickly, so hopefully you're not falling behind. But that is the basic idea of how to find a force vector, so hopefully not too bad. Now, R. R is the tricky one. And the interesting thing about this is that, again, we can use any r we want. Well, I shouldn't say we can use any r we want. We can use any r that goes from the point in question to the force's line of action. So we could do an ROA or an ROB. Both of them will turn out to be exactly the same. So you can do either one, but I think I'm just going to go ahead and do RAB just for illustration purposes. So I'm going to do, that's completely arbitrary, I just wanted to do that one for whatever reason. So that vector, and notice, this is a displacement vector, not a unit vector, so I don't divide it by its, just like if you recall our previous discussion of moments, the distance from the force is very important, so we don't want to use a unit vector, we need to actually use the full united vector with its magnitude baked in. So from 1 to 2, this is 1 meter. From 2 to 3, that's 1 meter. And from -1 to -2, that is -1 meter. So such an exciting vector. So 1, 1, -1. So now let me just go ahead and copy that. So we have that. Actually, you know what? I might go ahead and do this in exact form. Let me go ahead and get this, switch that calculator around and get this in exact form. I think that might be a little bit better in this case. So, let's see, let's put this calculator into exact mode. And so this is actually, yeah, we can go ahead and do this in exact mode. This is 20 over root 17, comma, 30 over root 17, comma, -20 over root 17. And I will need to transcribe this on the next page. So R, and I'm going to create a little table, the I, the J, and the K for each of these. Hat, the components. And then the R, my R, A, B, and my F. So the components of the R were 1, 1, -1. 1, 1, -1, and the F was 20 root 17, 20 over root 17, 30 over root 17, and -20 divided by root 17. And now I just need to find the cross product. So R cross F, I'm going to go ahead and write this out long form showing all of my work. Now, you don't necessarily always need to do this. A lot of the times you can simplify a lot of this by doing some of this in your head, but I'm going to do the full long form just so everyone's clear where everything's coming from. So again, I like to leave myself lots of space. This is a horrifically inefficient use of paper, but this is digital, so oh well, whatever. I, J, and a K. Now, also, notice I add my X and my Y and my Z terms are positive, but I just automatically tack on a negative into the J term. And now that of course doesn't mean the J term is always negative. This just means that whatever sign we get in here will end up flipping. So if it's a positive, it'll end up negative. If it's negative, it'll end up positive. Okay, so I'm going to have -20 over root 17. So this times 1. Actually, just I'll do -20 over root 17 times 1 minus 30 over root 17. 30 over root 17 times -1. So we'll try very hard not to make a stupid math error, which is certainly possible, so you have to be careful with this. So again, -20 over root 17 times 1 minus 30 over root 17 times -1. Now for the J, that's going to be 1 times -20 over root 17, and then minus 20 over root 17 times -1. Times -1 here. This times this. And then the K, for the K, I'm going to have 1 times 30 over root 17. 30 over root 17, and then minus 20 over root 17 times -1. So we're getting a lovingly beautiful equation here. Probably should have done these in brackets. In fact, let me do that. Let me just change that up a bit. Just so there's not too many parentheses floating around. Bracket, bracket, bracket. Okay, so now I'm going to keep working on this. Maybe do this and move this to a single line vector equation. So this is going to be negative 20 over root 17. Negative 20 over root 17. Actually, I'll still do it multiple lines. I'll keep it a little bit neater. Negative 20 over root 17 plus 30 over root 17. For the I, and I know this is a bit superfluous. I am just trying to be very meticulous and above and beyond in showing every scratch of my work, basically, for this. Negative 20 over root 17, and then plus 20 over root 17. So in this case, it looks like the j component will actually be 0. The final j component is going to be 0 because those two things will cancel out. And then plus 30 over root 17, 30 over root 17, and then plus 20 over root 17. Plus 20 over root 17. Let's see. Oh, wait. There appears to be some sort of error on this. Oh, what do you know? There is an error on this. Look at that. That should be a positive one. So if I cover up the k, 20 over root 17 times 1. Uh-oh. That's an error. That'll get you in trouble. Okay. And hopefully there are... Let me double check all these just because. So negative 20 over root 17 and then plus... on the for the I, negative 20 and then plus 30. Yep, that looks good. For the J, negative 20 and then basically plus the 20, plus 20. Yep, looks good. And for the K, 30 minus 20. Okay, that looks good. Assuming I made no other math errors, which is certainly possible. So then we'll have basically at the end 10 over root 17, 10 over root 17 Newton, and the units here would be Newton meters in the I, and the J, it just cancels out, plus 10 root 17 Newton meters in the K. Or you could also write this as 10 over root 17, comma 0, comma 10 over root 17, and then with Newton meters out front. There are any number of ways we could write this and report our answer. So, and that really is the basic process. I mean, we can work through a lot more different forms of this. Now, some of the examples can be tricky, especially when you look at 3D drawings where they ask you to find fairly complex arrangements of parts and shapes, and teasing out the geometry and playing with the drawings can be quite challenging cases. But really, this is the basic process. Once you have the basic idea of how to find a moment, mathematically it really isn't too difficult. Too difficult, not difficult. Too difficult. Almost getting a drawl there, but anyway, I've been in Texas too long. Or is there such a thing? Anyway, so again, once you have the basic method, the rest is fairly easy. The rest is not too bad. So once you have that, you just find, if you want to find the moment of a force about a point, all you really do is you find your displacement vector, again, which the displacement vector is from the point where you want to find the moment about to anywhere along the force's line of action. It can take some doing. It can be a pain in the butt to actually suss out all the geometry and work through the trig sometimes if you have trig involved, to get the components and get the vectors. Just like when we looked at force vectors and displacement vectors before, the hard part can just be sometimes just figuring out the geometry. And so it can be a lot of work, it can be a lot of plugging and chugging and things like that, but ultimately it really isn't too bad. Finding a moment out about a point is not conceptually difficult, but actually working through some of the more complex problems can certainly be tricky. Okay, so I think that'll do it for this part of the lecture. In part 4, or I guess in the next part, which I believe is part 5, we will be moving on to the final part of the lecture, and there we will learn how to find the moment of a force about not a point, but about an axis. Alright, so that'll do it for this portion of the lecture. I hope you all enjoyed this. Hope you found this a bit illuminating, or not, at least not too confusing. I'll see you all soon for part 5. That'll do it for now, and as always, thank you.